Hello. So welcome to this class, and we are going to continue about the solid state physics course. And in the last part of the course, what we basically did was to cover the structure of the solid. So the mainly we talked about crystalline solids. So let us make the heading. So we talked about crystalline solids. So, in crystalline solids, we mainly talked about the iron cores or the nuclei. So, we talked about how the crystal lattices are mm, um, arranged into crystalline shapes, which are shapes which have discrete translational symmetry. So, let us do a very brief recap of what we did and what was the purpose of doing that. So, discrete translation of a crystalline solid. That is what makes a solid crystalline. So there are repeating units which are called unit cells. And due to this repeating unit, due to the nature of Fourier transform, we got something called also a reciprocal lattice. So, and this unit cell and this translational symmetry, discrete translational symmetry, sorry. So, discrete translation symmetry has, so that's why it has a unit cell, it also has a lattice, and it has lattice vectors. It has lattice plus basis. Unit cell is lattice plus basis. And from the unit cell, due to the periodicity, we also got a reciprocal lattice, right? So, um, and then we motivated the reciprocal lattice because reciprocal lattice, at least according to my experience when I was a student, then I found that the reciprocal lattice concept was very ad hoc, as in I did not understand that why we would need such a thing, because it's not something physical, it's a mathematical construct. So we actually ended up, or we successfully described or motivated why we need the reciprocal lattice and why it is a very good mathematical language, I would say, or a mathematical formalism to explain the crystallography data, and it also gives a backbone to various theories which rely on this translation symmetry, which results in this reciprocal lattice because of Fourier transform, right? So we also saw that thing, and we saw that how this reciprocal lattice language will connect two dots, the Lawyer's condition and the practical Black's law. And we also saw that how Fourier transform will automatically give you some reciprocal lattice formalism. And we also talked about how the reciprocal lattice of FCC and BCC will look like. So um, that is everything that we talked about. But we also talked about form factors, we talked about structure factors. But while we talked about all of this, we kind of assume, so let us give an example. So we assume that, let's say it's a 2D lattice, and there is an atom A, there is an atom B, there is, yeah, that is it. Maybe, yeah, this is the basis. Add the lattice plus basis. Lattice is a square lattice, and basis is 0, comma 0, and half, comma half, right? Okay. So now, what we are assuming here is the atoms are concentrated into these points, right? And most of the, it's a surprising thing, most of the properties of the unit cell rather does not come from these fixed points, or these are kind of the nuclei for the plus the fixed electrons, right? So these are the atoms, but they come from some free electrons that are floating around in the lattice. So most of the properties, for example, electrical conductivity, heat conductivity, like let's say why the metal is shiny, so like optical properties, all of this is a result of the free electrons that are there in the unit cell. Okay. Um, so today we are going to see that how actually to go about modeling these free electrons into the reciprocal lattice formalism. And today we are not going to start complete the like rigorous approach of the models, but what we are going to do is rather um, we will motivate that why this free electron thing was like motivated, even as in like how people could know that okay, then there is a lattice and there are atomic centers, but there are also free electrons which are just hovering around. Okay, so um yeah, so that is what we are going to do. We in this class it will not be a very formal rigorous class, but it will be rather an experimental motivation of why eventually free electron were established free electron were established as the major contributor to the solid state properties. Okay, so that is what we are going to do. Before that, let me give you some motivation, because like otherwise we don't understand why should we study free electrons. How could people come up, how could people figure out that okay, this is the case, that the free electrons are responsible for most of the solid state physics properties? So for that we need to go back in time. So we are going to start around 1800, right? So this is a very fascinating kind of piece. So we know about Dalton's theory, who actually told that atoms are the smallest unit of any supercell or any unit cell. Sorry, any solid or any liquid or any matter for sake. So there are no more smaller particles in the atoms. So that thing was later disproved. So the indications were already coming by Rutherford's experiment, who found out that the most of the mass of an atom is concentrated in a single piece, in a single small dot or a small area, and the charge is, I would say, the charge is spread around in an atom, but like a very huge chunk of the charge is actually concentrated in a small area. So that was giving some indication that okay, the atoms are not like some billiard balls, but they have internal structures. Um, so the electronic models we will study will be motivated by this formalism that okay, the electrons itself were not discovered before 1897. So that's a long time, right? Um, and the electrons will actually become the unifying language of how electricity and heat is conducted. So that's why actually all the theories we are going to study, Drude model, for example, there is a model called Sommerfeld model. So these are models of free electrons. These models were specifically designed or made or proposed to solve some imminent problems which were being seen into the scientific community on that days, on that period. So it is like around 1890s to 1900s, right? So before that, mm, what we will see is before this time, like around 1850s, what was the case? So there were two properties, heat and electricity. Okay. So these are completely different things, and they were seen as completely different for obvious reasons, because heat could flow in a free medium. Let's say there is a hot bulb and you are standing somewhere else and you can feel the heat. But electricity does not flow through everything, right? Conduction through an empty medium, conduction through an empty medium. Okay. So when we go on, then we will see that heat and electricity, they were different things. Heat felt hot. Electricity, when it comes to electricity, you will feel shock. So there was the sensations themselves were different, and people back then, the scientists back then, did not have a very good idea of how heat and electricity are correlated, and they did not have any idea of how the inner workings of solid state or any matter works. So they just assume that heat and electricity, maybe they are separate things, and they called it caloric. So heat was called caloric, and it was called like electric, for example. So what they said that the scientists of that time, for example, 1850s to 1900s, right? So they thought that this is a fluid, massless fluid, and this is also massless fluid. Okay. So, but these fluids are different. So there can be two types of electric fluid, plus fluid and minus fluid, because people were already doing experiments with, let's say, rubbing silk in a um, glass rod. So when you rub silk in a glass rod, one will get positively charged, one it will get negatively charged. So people kind of thought that it's some kind of fluid that's being transferred from one part to the other part. So it's basically higher water level and lower water level. And so they kind of thought electricity itself as a fluid which flows through the atoms. It's like a invisible massless quantity or an entity which is not inside the atom, but it is kind of flowing through the atoms. So that's what electricity is. Similarly, caloric was thought of as a fluid, just like electricity, and different theories were formulated that okay, when you touch hot body and to cold body, then the fluid flows from the higher region to the lower region. So that was kind of the theory that we had about heat and electricity. So heat was thought of as so how were they broken? As in, we obviously know now that heat and electricity don't work like that, right? Heat is basically the kinetic energy, and electricity is flowing of electrons or charged particles. So let's come to heat. So the heat as a fluid was mainly broken by two experiments. The first experiment was done by, so what he did was he took this is the approximate explanation of the experiment. So he took an iron rod and he put it in a water container, and he put two horses, horse one, horse two, to both sides, and the horses were running, and the this thing was rotating. So that was the main setup of the experiment. And when it did that, so what they found is eventually the water heated up and started to boil. So told that okay, if we think heat as some fluid which is contained in a body, then how can a body which is just moved can get so hot that it can make a water boil? So it should not be. I mean, so the analogy was that if it was a fluid contained, then there will be finite amount of fluid, right? So there will be not so much amount of fluid that can make the water boil. So then he kind of figured out that heat has something to do with the motion of the horses. So he told that I can't believe that heat is some fluid, but it kind of correlated with motion. So people told that okay, maybe not. People were not very convinced, but the final quantitative experiment was given us by Joule, who what it did is he dropped very heavy brass balls, and he had a pulley, and he had some this kind of pulley in a water, in a sealed water container, and he had a thermometer. So when the brass ball fell, then this thing would rotate and the water would heat up. And he said that he kind of found that for when the ball goes from here to here, it loses some energy, it loses some mechanical energy due to gravity. The same mechanical energy is quantitatively transferred to the water. So for the same fall, no matter how many times you repeat, the water will get heated up the same exact same amount. So that proved that okay, it's not only qualitative, but there is a quantitative um, connection between heat and motion. That proved that is the famous source of the Formula 1 calorie equals to 4.18 joules. And this heat and motion, they were the same thing. So it was proven that heat of a body is just the microscopic motion. Okay. Okay. So that was the story of heat. So heat is like now it was proved that heat is not a fluid. Heat is motion. Okay. Now let's come to electricity. So when we come to electricity, then we go to J.J. Thomson's experiment, who discovered electrons. How he did? He sent a electric ray and he applied a magnetic field, and he saw that the ray actually bent. So he calculated the radius from the radius of the curvature. He calculated the mass of these particles, and they were approximately 1 by 1800 mass of a proton, of a mass of a proton, the m of the particles were. So they said, J.J. Thomson he inferred from this experiment that there are smaller particles in the atoms which are smaller than the protons, or smaller than the hydrogen atom rather. So then protons and electrons, they were separately, they were not formulated, but he saw that okay, there is some particle which is actually weighing 1 by 1800 times of hydrogen atom. So that means that it is smaller than an atom and it is contained in an atom. So and then it was proven that electricity also is not a full fluid, rather electricity is a flow of particles. Okay. Okay. So now another thing that was the weirdest thing was Wiedemann-Franz law. It uh it found that the if the electric conductivity was high for a metal, the heat conductivity was also high. And the electric conductivity, let's say it's sigma, and heat conductivity is kappa. Sigma by kappa was directly proportional to temperature, and if you took different metals with the same temperature, then the sigma by kappa were more or less constant. So it was shown that at a given temperature, the heat and the electricity are conductivity, they go hand in hand. So they are, it was uh, being made clear that they have the same mechanism. The heat and the electricity have the same mechanism of transferring. So from that, so what we know, that heat is motion, electricity is charge, charged particles flow, and heat and electricity are probably conducted by the same mechanism. So what Drude did was, so the first model we are going to start in the next class is Drude's model. Drude basically told that, okay, fine. He already had access to the kinetic theory of gas, kinetic theory of gas. And what he did was he told that electricity is, so he rebranded these three questions, these three statements as el- electricity, electricity is the motion of electrons, motion or drift of electrons. Heat transfer is the transfer of the kinetic energy of electron via diffusion. So he considered that electrons inside a metal, so inside a metal, he considered that there are centers, there are nuclei, but there are also electrons which are freely flowing. So they are consisting of like a gas. They don't interact with each other, they don't collide with each other, they only collide occasionally with the positive charges. And so he considered this as a free electron gas. So it's like an ideal gas made up of electron. Okay. And by that he could actually connect heat and electricity transfers. And he could say that, okay, these things are done by the same free electrons which are freely flowing throughout the lattice, throughout the material. They don't feel they don't feel the attraction of the ions. They don't feel the attraction of or repulsion of other electrons. They don't collide with each other. They don't interact with each other. The electrons only collide with the positive ion centers occasionally, changing their direction or changing their momentum. So that is the Drude model. And we in the next class, so all of this discussion that we had was to just to see that why Drude model was like so celebrated. It's a celebrated model, and um, and it is like a well motivated model which came at a right time. So this is the discussion that we are going to have, that in the next class a more mathematical treatment would be done of the Drude model, and we will see that how it kind of explained a lot of properties of metals qualitatively, and it could unify the electricity and heat transfer also. And um, and we will also see that what were the limitations of Drude model and how Sommerfeld model could partially correct for those limitations. So see you in the next class. Best of luck.